Hello, students. Welcome back to Engineers Academy. Do hit the subscribe button if you are here for the first time. Now, we are going to solve these two problems which are related to this figure. So, the problem says that the 150 kg bucket is suspended from end E of the frame. Determine the average normal stress in the 6 mm diameter wire CF and the 15 mm diameter short strut BD. So, we are asked to find the average normal stress in this wire and the average normal stress in this strut in the first part of the problem. And in the second part of the problem, again, the same bucket is suspended from end E. If the diameters of the pin at A and D are 6 mm and 10 mm respectively, determine the average shear stress developed in these pins. Each pin is subjected to double shear. So in the first problem, we are asked to find the average stress in this wire and this BD strut. And in the second problem, you are asked to find the shear stress in the pin at point D and in the pin at point A. So now the strategy for the solution of this problem is that first we will find the force or the tension in this wire, the force in this BD member, and for the shear stresses we must find the support reactions at A, and then we must find the force on the pin which is at A, and then we must find the force in the strut, because that strut force will be the force of the strut on the pin. So first of all, to find the tension in this wire, what I will do is that I will cut this wire and I will represent the force of this wire, and I will consider the whole diagram, right? So let me draw the free body diagram. So for that I will cut this wire, and for wire we will have, let's say, this is the FCF, the force in CF wire, and at A we will have the support reaction. So let's say at A I have AX, and we will have the vertical support as well. So let's say this is AY, and at E we have the weight of the bucket. So the weight of the bucket is going to act vertically downward, which is 150 times 9.81. So 150 times 9.81 is 1471.5. So this weight is 1471.5 Newton. And similarly, we can resolve this FCF into its components, since it is making 30° with this vertical line. So we will have one component in this direction and we will have one component in this direction. So this component is the cos component, since the angle is made with the vertical, and this one will be the sine component. So let me represent those components. So we will have, this one will be FCF sine of 30, and the vertical component will be the cos component. So this will be FCF cos of 30. Now if we consider this whole frame, then this will give us FCF and this will give us AX and AY if we apply the equilibrium conditions. So if I apply the sum of the moment about point A equals to 0, counterclockwise moment is assumed to be positive. Now as you guys can see that this component is passing through that point A, it's not going to produce the moment because its moment arm from that point A is equal to 0. So this component is producing the moment about point A in this direction, that is in the counterclockwise direction. So we will write FCF sine of 30, and the moment arm of this FCF sine of 30 from that point A will be this vertical distance, which is 1.2 plus 1.6. So this is 1.8. So multiply by 1.8. Similarly, the weight of the bucket is producing the clockwise moment about point A. So we will write minus, because the clockwise moment is minus 1471.5, multiply by the perpendicular distance. So this is the perpendicular distance. So this will be the moment arm, which is 0.6 plus 0.6. So this is 1.2, and this is equal to 0. So if I bring this to the other side of equation, so we will have the equality here. So let me have the equation like this. And then from this we can write that FCF will be equal to this divided by sine 30 times 1.8. So we can say that FCF is 1471.5 into 1.2 divided by sine of 30 multiplied by 1.8. So this is 1962. So from this we can say that the the force in the wire is 1962 Newton. Similarly, if we apply, considering the whole frame, if we apply the sum of the forces in the x, that must be equals to 0. Towards the right is our positive x. So then we can say that ax is in the positive x. We can say this ax is in the positive x. So we will write plus ax, and then we have this sine component of FCF, which is in the negative x. So we will write minus FCF sine of 30, and FCF value is now 1962. So 1962 sine of 30, this is equal to 0. So this means that x is equal to the sine component of FCF. So if we bring this to the other side of equation, it will become positive. So we can say that ax is equal to 1962 sine of 30, which is equal to 981. So ax is equal to 981 Newton. Similarly, if we apply the sum of the forces in the y, that must be equals to 0. Upward direction is considered to be positive. So we have ay in the positive y direction, so plus ay. We have the cos component of FCF in the downward direction, so we will write minus FCF is 1962 cos of 30, and then we have the weight of the bucket in the downward direction, that is in the negative y. So we will write minus 1471.5. This is equal to 0, and from this we can say that ay is equal to, so we can say ay is equal to this, right? So the equation will look like this. So from this we can say that 1962 cos of 30 plus 1471.5. So this is 3170.64. So 3170.64 Newton. Now the resultant force, we can say that the resultant reaction HA will be equal to the sum of AX and AY. So AX, this is AX plus AY. So this will be the resultant like this. So the resultant is going to act in this direction. So this is the resultant force reaction at A. So the magnitude of that resultant will be, we can say that the resultant magnitude will be AX square plus AY square under the square root. So you guys can always use the Pythagoras theorem. So these are the components of the resultant, ax and ay. So we can say 981 square plus 3170.64 square. This gives us 3318.93. So the resultant reaction force at A is 3318.93 Newton. So this FCF is the force in the wire, and that is the support reaction at A. So this is the reaction of the pin for on the frame, right? This A. So if this is the reaction, then the action on the pin will be in this direction. So the force which is applied on the pin at A will be in this direction, and the pin as a reaction is going to apply the force in this direction. Similarly, since we want to find the force in this FBD as well, since we want to find the normal stress in this BD strut as well, so what we will do is that we will consider this CE part of the frame. So if I draw the free body diagram for CE, so we will have the free body diagram will look like this. Somewhere here we will have C, here we will have D, and here we will have E. Now at C we will have support reaction. So let's say I have CY and CX, let's say, and at D we will have the strut force on that CE member. So we will have the FBD. We will have FBD, the force of this strut on that pin at D, or we can say at joint D. And at E we will have the weight, right? So at E we will have the weight of the bucket, which is acting vertically downward. Let me write vertical, which is 1471.5 Newton. And these distances are, this is from here to here, this is 0.6, and from here to here, this is 0.6. Now we want to find FBD, right? Once we find FBD, so this will be the force on the pin at point D, since we want to find the shear stress on the pin which is located at D. So if we apply the sum of the moment, if we apply for this free body diagram, if we apply the sum of the moment about point C, that must be equals to 0. Counterclockwise moment is assumed to be positive. Now FBD will have two components, so we will have one component of FBD in this direction, and we will have one component in this direction. And from here we can see that this length and this length both are 0.6. So if we consider this as a right angle triangle, and if this is 0.6 and this is 0.6, then this angle is 45. So this means that FBD is making 45-degree angle here. So this angle is, we can say this angle is 45. So if this is 45, then this is the cos component, this is the sine component. So we can say that this is FBD sine of 45. Now we want to find the sum of the moment about point C. This component, the cos component, is passing through C. Its moment arm from point C is 0. It's not going to produce the moment about point C. So this means that this component is producing the counterclockwise moment about point C. So we will say FBD sine of 45. This is producing the counterclockwise moment, and the moment arm of this component from that point C is 0.6. So we will multiply it with 0.6. And similarly, this weight is producing the clockwise moment about that point C. So we will write minus, the weight is 1471.5 multiplied by the perpendicular distance, which is this distance, which is 1.2. So we will multiply this with 1.2. This is equal to 0, and FBD, the normal force in that strut BD, is 1471.5 into 1.2 divided by sine of 45 into 0.6. So let's find this. 1471.5 multiplied by 1.2 divided by sine of 45 multiplied by 0.6. So this gives us 4162. So this is 4162.03 Newton, right? So this is the force in that strut, right? So now for in the first problem, we were asked to find the average normal stress in the 6 mm diameter wire and this strut, right? So we can say that the average normal stress in wire CF will be equal to FCF divided by the area of the wire. So FCF is 1962, right? So from here we can say that this is 1962. So 1962, and the diameter of the wire is 6 mm, right? So divided by pi divided by 4 into d square, so 0.006 square, right? Or we can say that 6 mm divided by 1000. So let me write it like this, since we want to have the answer in meters, right? So 6 divided by 1000 square. So this will give us the average stress in that wire, the average normal stress in that wire. So 1962 divided by pi divided by 4 multiply by 6 divided by 1000 square. So this gives us, we can say that this is 69.39, or we can say 69.4 megapascal, because if we shift the decimal place 6 digits, then this will be 69.4 megapascal. Similarly, since we want to find the average normal stress in the strut, so the average normal stress in the strut, so the strut is BD, right? So this is the strut. So the force in the strut will be opposite to this FBD. So we can say that this FBD, this is the force of the strut on this CE. So as a reaction, this CE will apply the opposite force on the strut BD. and this means that this BD member, it's a two force member, so it is in compression. So this means that the average normal stress in BD will be compressive stress, right? So we can say that this will be FBD divided by the area of the strut BD. So FBD is 4162.03 divided by the area of the strut, which is pi divided by 4, and the diameter of BD is 15 mm. So divided multiply by 15 divided by 1000 square. So 4162.03 divided by pi divided by 4 multiply by 15 divided by 1000 square. So this gives us, so this is 23.6 megapascal. Again, if you guys count the number of digits on the left of the decimal place in the calculator, so we have 6 digits. So if we shift the decimal place 6 digits, then this will become megapascal. So 23.6 megapascal. Now we want to find the shear forces. So the shear force in the pin at A. So let's say if I draw the pin at A, so let's say this represents the pin at A. So again, this is, as I have told you, that this resultant is the reaction force which is provided by the pin, or we can say this is the reaction applied by the pin, right? So as a reaction, or we can say as an action, there will be a force on the pin in this direction. So we will have, if this is the pin at A, then we will have the force in this direction. If we look it from this side, then we will have the force on the pin at A in this direction, and the magnitude of this force will be equal to that A. This will be the same force of magnitude but opposite in directions. That will be 3318.93 Newton. And as you guys can see from here, from the side diagram, that the this pin will be supporting shear forces at two cross sections, right? Because it is subjected to these two, it is supported by these two brackets. So if there is a force, so there will be two shear forces. So the problem says that each pin is subjected to double shear. So we will have the double shear forces on two of the cross sections. So we will have VA here and we will have VA here. So we can say that we will have the shear force on this cross section. This will be VA, and we will have VA here as well. So now if we apply the sum of the forces on the pin at A along this direction, so we will have, if we apply the sum of the forces along the vector A, or we can say along the unit vector A, this must be equals to 0. So we can say that 2VA, if this direction is considered to be positive, so we will have plus 2VA minus that A force. This must be equals to 0, and from this we can say that the shear force on the cross section at pin A will be equal to A divided by 2. So A divided by 2, and now A is, we know that this is the A force, which is 3318.93. So 3318.93 divided by 2. 3318.93 divided by 2, this gives us 1659. So VA is equal to 1659.47 Newton. Similarly, we want to find the shear force in the pin at D as well, right? So as you guys can see that the strut is applying the force on the pin at D in this direction. So again, we will have the same free body diagram, but now we will have FBD here. So we will have, let's say that this now represents the pin at D. Now FBD is acting on the pin in this direction. If you guys look from this side, then FBD is going to push the pin, right? Since FBD, the strut is in compression, right? So we will have FBD, and FBD is, we know that this is 4162.03. So we can say this is 4162.03. Again, the pin at D is also subjected to two shear forces. So then we will have one shear force we will have VD on this face, on this cross section, and we will have VD on the other cross section as well. So again, if we apply the sum of the forces in this direction, right? So the sum of the forces uh, along the unit vector of that BD, that must be equals to 0. So we can say that FBD, so FBD minus 2VD, this is equal to 0. And from this we can say that VD is equal to minus 2VD is minus FBD, minus will become positive, and VD will be equal to FBD divided by 2. And similarly, we know FBD. So FBD is 4162.03. 4162.03 divided by 2. So 41 divided by 2. This gives us 2081.02, let's say, Newton. Now, once we have found the shear forces, then we can find the average shear stresses at pin A and at pin D. So we can say that the average shear stress in pin D will be VD divided by the area of pin at D, right? So the area of pin at D. So now VD is 2081.02, and the problem says that that the diameters of the pin at A and D are 6 mm and 10 mm. So the diameter of the pin at D is 10 mm, right? So 10 mm, right? So this is the diameter of, we can say, this has a diameter of 10 mm, and we can say diameter is this symbol, and similarly the diameter of this is 6 mm, right? So we can say this is 6 mm, right? This is the dia of this pin is 6 mm. So now we can say that this will be pi divided by 4. Dia is 10, right? So 10 divided by 1000 is, we can say, 0.01 square. This is equal to 2081.02 divided by pi divided by 4 into 0.01 square. So this gives us 26.5 megapascal. And similarly, the average shear stress in pin at A will be equal to VA divided by the area of pin at A. So now VA is this, which is 1659.47 divided by the area of pin A. So the diameter of the pin A is 6 mm. So we will have pi divided by 6 mm divided by 1000. So that will be 0.006 square. So this is equal to, so this is 1659.47 divided by pi divided by 4 multiplied by 0.006 square. So this gives us 58.69, or we can say 58.7 megapascal. So this is the shear stress in pin A and pin D, and these are the normal average stress in that wire. This is in the wire, and this is in that BD strut. So this is the solution of these two problems. I hope this will help you in your learning. Let me know in the comments if this helps. Do subscribe Engineers Academy for the solution of such more problems from Mechanics of Materials by R.C. Hibbeler.